Networking perspective. From a networking or protocol design point of view, any wide area routing protocol must fulfill, to some extent, the following requirements. For reason of trust, scale, and robustness, the routing protocol must be distributed carried out by the ACEs themselves. In order to reduce routing state, the routing protocol must use destination-based forwarding, i.e., all routing decisions must be based solely on the packet's destination. Each ACES has a single next hop for the destination D, and the resulting route allocation TD equals to the set R1, R2, R3, and so on to Rn forms a confluent tree to the destination D. The routing protocol should be adaptive, adjusting to the current network topology without relying on any prior topology information. The routing protocol should be time-efficient, communication-efficient in its use of communication between the ACEs, and space-efficient in its use of the storage space that each individual ACE needs in order to participate in the protocol. These requirements are satisfied by each of the common routing protocol designs, namely distance vector, link state, and the path vector, although these designs differ in their space requirements. However, interdomain routing has one additional requirement. The routing protocol must produce loop-free routes even while individual ACEs make autonomous decisions about which routes are preferable. Of the common routing protocol designs, only path vector satisfies this requirement. As a result, the current standard protocol for Internet interdomain routing, the Border Gateway Protocol (BGP), is a path vector protocol. To see why path vector is a suitable design choice, we describe BGP in more detail. BGP allows adjacent nodes to exchange information through update messages that announce newly chosen routes. See illustration in Figure 14.3. A route announcements contains the entire path to the destination, the list of ACEs in the path. A path contains a path vector protocol, like most other routing protocols, computes routes to every destination ACE independently, so we can focus on routes to a single destination D. The route computation process is initialized when D announces itself for its neighbors by sending update messages. The rest of the routing tree to D is built recursively, as knowledge of how to reach D propagates through the network via subsequent update messages. We assume that the network is asynchronous, meaning that the arrival of update messages along selective links can be delayed. The routing protocol process at a particular node I has three stages that are iteratively applied. 1. Importing routes. Routes to D are received via update messages from its neighbors. Node I has an import policy that specifies which of the routes it is willing to consider. All such importable routes are stored in an internal routing table. At any given time, I's internal routing table contains the latest importable routes. 2. Route selection. If there is more than one route to D in the routing table, i.e., more than one of I's neighbors has announced an importable route to D, node I must choose one expressing a local preference over routes. 3. Exporting routes. Whenever there is a change to I's best route, it announces the newly selected route to some or all of its neighbors using update messages. Node I has an export policy that determines for each neighbor J which routes it is willing to announce to J at any given time. AS autonomy is expressed through the freedom each AS has in choosing its routes, its import policy, and its export policy. These choices are based on local policy considerations and need not be coordinated with any other ACE. The inclusion of the entire path in route announcements allows ACEs to avoid routes with loops even while making otherwise arbitrary policy choices. Link state or distant vector routing protocols can avoid loops only if all ACEs use the same criterion to choose routes and thus do not support autonomy. One design requirement that explicitly listed here is convergence. Clearly, the routing protocol should eventually enter a stable state in which every node prefers its currently chosen route to all others in its routing table, and all routing tables reflect the current route choices of its neighbors. Moreover, we would like the protocol to be robust. Convergence for every AS graph obtained by removing any set of nodes and links from the original instance. Unfortunately, while the path vector form of routing prevents loops, it does not ensure convergence. The routing announcements can enter a persistent auxiliary state. Consider the simple example depicted in Figure 14.4. Both nodes 1 and 2 would rather send traffic through the other source node than send traffic directly to the destination. Let us now simulate the execution of a path vector protocol in the worst-case scenario. The computation is initialized when D announces itself to its two neighbors. Nodes 1 and 2. At this point in time, these direct paths are the only routes available to D. Hence, 1 and 2 will choose the routes 1D and 2D, respectively, and inform each other via update messages of their selected routes. Upon receipt of these update messages, nodes 1 and 2 will change their selected routes to, respectively, 1-2D and 2-1D. However, now that none of the direct routes is being used, the indirect routes are no longer viable, so 1 and 2 are forced to return to their former routes 1D and 2D, and the oscillation continues indefinitely. Note that if the network had started with node 1's choosing and announcing 1D, having not yet seen an announcement of route 2D, and then node 2 had chosen to 1D, having seen route 1D announced before it chose and announced its own direct route 2D, then no further changes would occur and the network would be in a stable configuration. Thus, convergence and oscillations can depend on timing. A large body of networking research has addressed the problem of providing sufficient conditions on routing policies for the convergence of path vector protocols. There is an inherent trade-off between the desired autonomy at the local level and the robustness in the sense defined above at the global level. However, there is a non-sufficient condition on policies called no dispute wheel that guarantees robust convergence, while allowing fairly expressive local routing policies. Any network instance on which a path vector protocol might oscillate contains a dispute wheel and, more importantly, the absence of a dispute wheel means that the instance and every subinstance of it have unique stable route allocations to which the routing protocol converges, i.e. no dispute wheel implies robustness. The following definition provides an equivalent sufficient condition. Definition 14.3 defining two relations on permitted routes. One, let R1 minus 1 R2 if and only if R1 is a subpath of R2 that ends at D. Let R1 minus 2 R2 if and only if there exists I in N such that R1 and R2 in P to the I and I prefers R1 over R2. Let slash equals to minus 1 union minus 2 star be the transitive closure of minus 1 minus 2. Note that slash is inherently reflexive and transitive. An interdomain routing instance has no dispute wheel if and only if R1/R2 and R2/R1 together imply that R1, R2 start at the same node. Informally, this is anti-symmetry of slash except that ties are allowed in evaluations. Let us revisit the example in figure 14.4. Recall that on this instance, path vector particles may oscillate forever. This anomaly is manifested by the following dispute wheel. 1d minus 1, 2, 1d minus 2, 2d minus 1, 1, 2d minus 2, 1d. So far, our discussion of interdomain routing has focused on traditional networking concerns. We now consider the problem from a mechanism design perspective.